Hi everyone, so today we're going to be discussing Coulomb's law. So Coulomb's law is a fascinating law that kind of discusses the idea that atoms experience a type of potential energy called electrostatic potential energy. And electrostatic potential energy is based on the idea that like charges attract. So let's say we have two atoms here. One is positively charged and one is negatively charged. When these two are brought close together, they will be attracted to one another. Coulomb's law also says that unlike charges actually repel each other. So, unlike charges will repel. So those are the two main ideas of Coulomb's law. And we can quantify everything from Coulomb's law into a neat little equation. So the Coulombic energy, which is just a fancy word for the potential energy between two atoms, that is going to be equal to a constant. And this is just a constant of proportionality. So multiplied by Q1, which is the charge on atom 1, multiplied by Q2, which is the charge on atom 2, and this is all going to be divided by R, and R is the distance between the two particles. So notice here how interestingly distance is actually inversely proportional to the potential energy between two atoms. So this means that as the distance gets smaller, distance is smaller, the magnitude of potential energy is greater. And vice versa for when the distance is larger. All right, so now let's actually start to create some energy ladders to depict this. So let's say that we have two atoms. One of them is positive, the other is also going to be positive. Call this Q1, we'll call this one Q2. They're separated by a distance of R. And then we're going to have a negative here, a negative atom here, a negative atom here, and they're separated also by a distance of R. However, this R is going to be much larger. So the distance between these two, E2 is actually, so we're going to call this one E2, and we're going to call this condition E1. So note here how the distance is much larger in E2. So when we're actually thinking about this in terms of Coulomb's law, let's write this out. So we have the energy of 1 is going to be equal to the constant multiplied by Q1 times Q2. Remember, this is all from the equation up here. And this is going to be divided by the distance of R. For E2, however, we could say that the distance is approximately 2 times here. So the blue R is approximately 2 times red R. So R is equal to 2 times red R. So what we're going to say here is E is equal to the constant times negative Q1 times another negative Q2 divided by 2R. And what we actually end up finding is that E2 is going to be much smaller, right? Because we're dividing by a larger denominator. So the potential energy of E2 is smaller than the potential energy of E1. And we can confidently say this because this is positive, right? Because we're multiplying a positive times a positive and dividing by two positives, so this is going to be positive. The same thing here. Negative times negative, well, this is just a positive times a positive divided by a positive. So what we're saying here is that the potential energy of E2 is going to be less than the potential energy of E1. And if we put this on a ladder, we can say that this is where E equals 0. And because it's positive, everything's going to be above 0, right? So we're going to do E2. And then we're going to have E1. And this is just saying that E1 has greater potential energy than E2. And conceptually, this actually makes sense. And we'll discuss why in a moment. So let's think about the conceptual idea of what it means to have positive and negative potential energies. So as we saw in this example, when two like charges interact with each other, we get a positive potential energy. So like charges have positive potential energies. But why? What does this mean? Well, this means that particles are pushing each other away. They really don't like each other. They don't want to be around each other. And what this means is that work is needed to bring the repelled particles together. Or in other words, the system is unstable and it gains stability by making the particles get further apart. So, further apart, we gain stability when that happens. All right, when two unlike charges interact, we get a negative potential energy. But what does this mean? Well, negative potential energy means that particles actually like being around each other, and this means that stability is gained as particles get closer. We consider this a stable system, and work is needed to separate the attracted particles. All right, so let's actually depict all of this information graphically. So let's have energy on our y-axis. And let's have distance on our x-axis. All right. Now, what has negative potential energy? It's when we have two unlike interactions. So, remember, this is going to be negative potential energy, and this upper portion is going to be positive potential energy. So let's actually make the positive in a different color. What we're saying with the negative potential energy is that there is going to be a more stable interaction as the particles get closer together. So let's have these white. Closer, further. So what we're saying here is that as the particles get closer together, we are generating a more stable interaction. So the potential energy gets more negative. Now, when we're talking about positive potential energies, we're saying that as the particles get further and further apart, we're gaining stability. And this is because their potential energy becomes less positive. So stable when further. So more or less positive potential energy. And notice that the energy goes to zero as the particles reach infinite separation. So as the particles become infinitely and infinitely more far away from each other, the energy of interaction is literally just zero because they're not interacting with each other at all. All right, so that's a little bit about energy ladders and these Coulombic attraction graphs, which I find super helpful. And actually, one more thing about this graph is that this is really just the equation that we discussed earlier, but in kind of a simplified form. So think of it as energy is equal to the Coulomb constant multiplied by 1 over x. So x is think of it as just the distance. And then this is our variable y, which is just the energy. And this is the constant. So hopefully you can see that inverse relationship between distance and energy from this graph. All right, thank you for listening.